dear students, now let's see another experiment in physics. Look at this. This is about verification of the law of parallelogram of forces and using it to determine the mass of a body. So, when you say law of parallelogram, let's quickly recall the theory regarding the law of parallelogram. If two forces act on a body, or if two forces act on a point like this, let's say this is F1, this is F2. And if the length of these lines and the direction of the lines are proportionate to the forces, then what we can do to find the resultant of these two, we have multiple ways of finding the resultant. You would have studied that in theory. Either you can use the equation or you can resolve it into components. Likewise, there are multiple ways of finding the resultant. One method to find the resultant of two forces is to complete the parallelogram having these two as the adjacent sides of the parallelogram, right. So, let me copy these sides. Right, let me draw it here, and then copy this side, draw it here. You know, when you say parallelogram, the opposite sides are parallel and equal. Parallel and equal. This is parallel to the other side and they are equal in length. Similarly, the opposite side, these two are also parallel and equal. Now, draw the diagonal that goes through the point where these two forces intersect. See, this is the point where the two forces intersect. Draw the diagonal through that. This diagonal will give you the resultant of F1 and F2. This is what we call law of parallelogram. If there are two forces acting on a point, draw two lines proportionate to the size of that, to the magnitude of those forces in the direction of those forces. Then complete a parallelogram having those two sides as adjacent sides. Then draw the diagonal that goes through the point where these two forces intersect. Measure the length of the diagonal, and you know the scale that you used already, the proportion, multiply by the scale, you will get the resultant force of F1 and F2. Clear? So, what we are going to see in this experiment is to verify this. After verifying this, we are going to use the same concept and find an unknown mass of a body as well. So, how do we verify? We have an apparatus in the laboratories . I will tell you what it means. Right. So, this is a wooden plate. On that, two pulleys have been fixed. So, we fix this board vertically, the wooden board, you fix it vertically, and then see what we do. Right. So, this is a thread. On the thread, what we do? We tie a weight here, let it be M1. We tie another weight here, let it be M2. And we tie another weight here, let it be M3. So, once you tie appropriate weights here and let it hang freely. Make sure these threads or the strings do not touch the plate, do not touch the board. They freely hang. Then I can say once they come to an equilibrium, initially like when you tie all these and leave your hands, they might just go up and down, and after a while they come to an equilibrium. When they are at equilibrium, let me mark the forces. Let this be the weight of this one, M1G, and this will have a tension of T1. This will have M2G, T2. M3G and T3. So, since all of them are in equilibrium, I can say T1 is equal to mg, M1G. T2 is equal to M2G, because there are no other forces acting on those particles. Only these two are the forces. That means they are in equilibrium. Then T1 and M1G are equals. T2 and M2G are equal. T3 and M3G are equal. Further, this is the same string. It goes up to here. If the tension here is T1, I can mark this tension also to be T1. If this is T3, this also has to be T3. If this is T2, here I can mark T2. But to mark like this, there has to be one condition to be satisfied. T1, if the same T1 if I have to mark here, T3 if the same T3 if I have to mark here, T2 if the same T2 if I have to mark here, there is one important condition that has to be satisfied. Do you know what that condition is? Condition is the string has to be light. That means it should not have its own weight. If there will be weight, then if it is T1 here, the tension here will not be T1, it will be something else. If this is T3, it will not be T3 here because of the weight of the string. Point to point, the tension will vary. Since it is light string, that means it doesn't have weight or the weight is negligible, we can assume this. Next, the string goes over the pulley, right? If it is T1 here, I can mark T1 here. Again, there is a condition for that. What is the condition? The pulley has to be smooth. There should not be any friction on the pulley. Pulley is smooth, then if this is T1, this will also be T1. T1. If this is T2, this will also be T2. T2. Clear? This is how the forces are going to be. Now, consider this point, right? It is in equilibrium under three forces. Let me draw the three forces now. You have T2 like this, T1 like this, and T3. T2, T1, T3. I know the value of T1, T2, T3. Why? T1 is equal to M1G. So, M1 is the known weight. G is 10, gravitational acceleration. So, M1G is known, therefore, T1 is known. M2G is known, therefore, T2 is known. M3G is known, therefore, T3 is known. So, I can draw these lines proportionate to those values. T1, T2, T3, I know the values. So, I can draw it proportionately. Now, listen. Let me keep this T3 aside. Keep the resultant of T1 and T2. I am going to combine T1 and T2 using the law of parallelogram. So, when I combine the resultant of T1 and T2, let's say, okay, let's first mark T3. Let it be here. If this is T3, now I am going to combine T1 and T2. This is T3. T1 and T2's resultant, can it be like this? Can it be like this? What do you think? No, it cannot be like this, because once you combine T1 and T2, then you are going to have only two forces acting on that point, which is the resultant of T1, T2 and T3. There will be only two forces acting on that point. So, these two forces, like equilibrium under two forces, only one possibility is there, that two forces must act at the same point. They must intersect at a point. The two forces must be equal and opposite. So, basically the two forces have to be on the same line of action. If T3 is vertical, T3 is a weight, right? Weight, and this line will be vertical. So, since T3 is vertical, R also has to be vertical. This is wrong. It cannot be possible. R cannot be angled to the vertical. So, how is it possible? How is it possible? Look, if this is T3, if this is T3, the resultant of T1 and T2, R has also be vertical. It also has to be vertical. It also has to be vertical through the same point. Can you see R? And this R must be equal to T3. Lot of conditions are there. Two forces equilibrium. The two forces must be acting on the same line of action, but they must be opposite. They must be equal in size. So, R and T3 must be equal, right? So, now come back to the experiment what we are going to do. We know T1, T2, T3. So, draw this line proportionate to T2. Draw this line proportionate to T1 and complete a parallelogram. Complete the parallelogram. After completing parallelogram, the resultant has to be, right, this is the parallelogram, complete the parallelogram, and then draw the diagonal, find the length of the diagonal, the scale you have used, so you can find how much of weight is indicated by this diagonal. The diagonal has to satisfy two properties. Property number one, diagonal has to be vertical. Diagonal has to be vertical. It can't be angled. I explain why. Second one, multiply by the scale and find out the force that is indicated by this diagonal. That force must be equal to T3. R and T3 are equal, right? So, the force indicated by this diagonal and the T3 is equal to M3G. T3 must be equal. So, once we do this experiment, if we can get the diagonal vertically and if the diagonal's force is equal to this middle weight, then we can say the law of parallelogram is verified. Clear? So, that's all we are going to do. After verifying it, what we can do, then second part of the experiment, there are two parts I said. Second part is finding an unknown weight. Put that unknown weight here. Remove this M3 and fix it here. Again, for some M1 and M2, balance this system. Again, draw the line for T1, draw the line for T2. Complete the parallelogram. Draw the diagonal. Measure the diagonal. Multiply by the scale. Now, we have already proven that gives this middle weight, right? Therefore, the diagonal will give us the weight on the middle string. Clear? So, this is what we call, what we are going to do in this experiment, verification of law of parallelogram as well as the finding an unknown weight. Clear? Let us see the materials and apparatus that are required for this. Parallelogram of forces apparatus, yes. An object of unknown. Parallelogram of forces apparatus means that's that wooden board with two pulleys and the string. Three known loads because M1, M2, M3 have to be known. Three known loads. A set square or a short plane mirror strip. Why do we need this? Now look at this. I said, okay, we have to draw a line parallel to this string, right? If this is the board, string is going to be a little forward. It's going to be, there's going to be some distance between the string and the board. So how do we draw the line on the board which is parallel to the string? We are going to use a set square or a mirror, a strip of mirror. When I do the experiment, I will explain you how the mirror is going to be useful here, right? So, for the moment, let's not discuss about that. During the experiment procedure, I will explain where this mirror strip is going to be useful. A half meter ruler, that's to measure the length. Drawing pins to fix the paper. We need a paper and we will be fixing the paper on the board because that is where we are going to mark the points, then draw the parallelogram. An A4 white paper and a 3-beam balance. 3-beam balance is not mandatory. Why we need the 3-beam balance is to double check, like unknown mass. After finding it using the parallelogram, you can measure it on a 3-beam balance as well, and then you can double check. So, it is not mandatory to have this in the experiment. Theory I already explained, right? This is what we are going to do. Couple of things understand. What are the possible errors we can get here? One very common error is that pulleys might have friction. We assume pulleys are frictionless and we do this, but pulleys might have friction. If pulley has friction, then if you have T1 here, the other side tension may not be T1. So, you are going to assume T1 is equal to this weight, but if the pulley has friction, it will not be equal. Then the parallelogram, you will not get it perfectly. Possible error number 1. Error number 2, now sometimes you may use, to keep the weight, you may use a plate like this. Or you might hang it. That might have weight, right? Imagine if I am adding 50 gram of weight. Suppose if this plate and this hanging setup has, let's say, 3 grams of weight, then I have to take T1 as 53 gram equivalent, right? Not 50 gram. So, many a times we might not measure the weight of these plates, which can give us an error. That you can rectify. How? There are two options for you. Either remove these plates and hang the weight directly on the string, which might be a bit hard. If not, measure the weight of these plates as well and add them with W1, W2, W3. Add them also, right? So, that's second possible error. Third possible error, the strings might have weight. Even though we assume they are light, they don't have weight, there will be a small weight for them, right? So, because of that weight, the tensions might slightly differ point to point. Those are possible errors in this experiment, errors. Theory I already explained. Verification of the law of parallelogram of forces. Once the parallelogram OABC is constructed using a suitable scale, if the value of the product of the length of OC of diagonal and the scale value is equal to the value of the load W3, and also if diagonal OC stays vertically, then the law of parallelogram of forces is verified. I told you there are two conditions. The parallelogram has to be vertical, and then measure the length, multiply by the scale, that should give you the weight that we used in the middle. Determination of the mass of a body, load W3 dash. Once the parallelogram OA dash C dash B dash is constructed using a suitable scale, the value of the product of the length OC dash of the diagonal and the scale value will be equal to the value of the mass W3 dash. Similar way, complete the parallelogram, measure the diagonal, vertical diagonal, multiply by the scale. That's why they say product of the length of the diagonal and the scale. That should give you the unknown mass that you hung in the middle, right? Look at the method. Fix the paper on the board. Place loads W1, W2 and W3 on the balance pans. Balance pans is those plates. Pull down the middle load a little and release and test whether it returns to the original position. Now, that is an important step. Now, you have fixed all the loads and you let it, stabilize. It has come to a stable equilibrium, fine. Now, pull that middle one from its equilibrium position, pull it a little bit, few centimeters, pull it down and see what happens. Pull it, release your hands. What should happen is, it might slowly go up to the original position. All three loads should come back to their original positions. If they come back like that, then the pulleys do not have friction. Pulleys friction is negligible. Suppose if you pull it and leave it, if it doesn't go back to its original position, if it remains where it has been pulled and left, then the pulleys have friction. Understand? Pulleys have friction, pulleys do not have friction. That's how we verify, right? So, this step is important to verify that pulleys are frictionless. Next, by placing the set square normal to the strings or the plane mirror strip below the string that I told you I will explain later. The string covers its own image and then mark the paper by 2 dots, the projection of each string. This, when I do the experiment, I will explain. Basically, how do we get the projection of the string on the paper? Remove the paper from the board and draw lines across the dots marked on the paper. Basically, the lines of those strings. Measure the masses of the pans and add to the relevant load. See, to eliminate the error that caused by the mass of those pans, one option you have, measure the weights of those pans and add that also to the weights that we have hung there. Choosing a suitable scale, draw OA and OB with lengths proportional to the value of W1 and W2. Complete the parallelogram OACB and measure the length of diagonal OC. Confirm the validity of the law of parallelogram of forces and in accordance with the above theory. Remove load W2 and place the given body, not W2, W3, the middle one, and place the given body, the unknown load. Repeat the experiment as before and using the same scale, not necessarily same scale, can be same scale, can be a different scale. Suppose if middle weight W3 is a very small one, then we have to change W1, W2 as well. Right, so according to the weight that you get, you have to adjust the other weights as well. Construct the parallelogram OA dash B dash C dash and measure the length of the diagonal OC dash. Deduce the mass of the given body in accordance with the theory. Right, so I already explained you the theory, I explained you how we are going to do the experiment. Now let's see whether we can do this experiment, verify the law of parallelogram of forces and find the unknown weight. Students, you can see I have arranged the apparatus that are required for this experiment. Look at this board, right, this is the main apparatus here. It is a drawing board with 2 pulleys connected to this. Can you see these are 2 pulleys? Right, this is the special apparatus that we use to verify this parallelogram of forces in the lab, right. In science labs you will be able to find this usually, right. So this is the first one, and we need a white paper, a sheet of paper to draw the parallelogram and to verify the rule. We have a meter ruler to draw the parallelogram. Careful when you are writing in the exam, if you write it as foot ruler, you don't get marks for it, right. Even though in the lab we may be able to draw the parallelogram with a foot ruler, for the exam purposes, if you write it as foot ruler, they don't give marks. So you have to write it as meter ruler or even half meter ruler. Half meter ruler means this is 1 meter length. There is another ruler, half of this, 50 centimeters length, that is also okay. And then, see, this is where we are going to hang the weights, right, threads and these plates, right. And this is a set of known weights, this is 50 gram each, these 2 are 20 gram each, this is 10 gram, so we need a set of known weights to do this. And this is the unknown weight. I have taken a stone of which I don't know the weight, right. So that's the unknown weight we are going to measure. A strip of mirror, when I do the experiment, I will show you why this mirror is used. The purpose of this mirror I will not be able to explain now. While the experiment is in progress, I will explain the use of this mirror. If you don't have the mirror, you can even use the set square. You can use set square or the mirror, either of it, and a pencil to draw parallelograms. This is all the apparatus that we are going to use in this experiment. Now let's see how we are going to make the setup and how we are going to do this experiment. Students, you can see I have fixed the drawing board on a vertical plane, right. The pulleys are already fixed on the board. The board is on a vertical plane, and I have fixed this sheet also on the board. Now what should I do? I should hang the strings and the plates so that I can put different weights and see. You can see these are the 3 plates and the strings connected. Let me put them over the pulleys. Right. There might be a small weight for these plates and these chains. Because of that, there is an equilibrium. But anyway, when we are doing the calculations, we are going to ignore the weight of these plates. Right? Okay. So what we do, check this carefully. The board is on a vertical plane and the strings do not touch the board. Can you see there is a gap between the board and the strings? And the plates also do not touch any surface. They are freely hanging. Okay. And also I already explained, we assume that there is no friction in these pulleys. Pulleys are smooth and frictionless. Right. What are we going to do? We are going to put some weight here. The moment I put a weight here, it will go down and there will be an equilibrium point at which the tension on this string will be equal to the weight of the mass that I added here. Suppose if I add 50 grams here, 50 gram means 0.05 kilograms, multiply that by gravitational acceleration, it will be 0.5 Newton. So if you add 50 grams here, 0.5 Newton is its weight. Then the tension on this string has to be 0.5 Newton. And same string comes over here, which means this string also should have the same tension. Condition, if the string has to have same tension on both sides, this pulley has to be smooth. Pulley has to be smooth and it should not have any friction. Yes, under that assumption. Okay. So let's add the weight and continue the discussion. So these are 50 gram each. Let me add a 50 gram here and another 50 gram here. Now this goes up. Let me add a 50 gram for that also. Right now there is an equilibrium 50, 50, 50. I can put any weight that is in equilibrium. Let me add another 20 to the middle one. I'll add another 20 here. So the point has come down here. Both sides now we have 50 each, 50, 50. Let me put a different one. Let's put another 10 gram here. It's 60 now. So the weights I have 50 gram on this side, 60 on that side, 90 in the middle. Right? You can have any mass that brings the system to an equilibrium is fine. And make sure the paper is fully utilized. See, now, since I have got this point here, I can draw the parallelogram in the full paper. See, imagine if you had the point somewhere here, then more than half of the paper will not be used. So having that in mind, put the weights such that it comes to an equilibrium. So again, see, this is 50 gram, 0.5 Newton on this string, 0.5, 0.5, 0.5. So up to here, the string will have 0.5 Newton tension. Here I have 60 grams. So this string will have 0.6 Newton. 60 grams means 0.6 Newton. All this way up to here, it will have 0.6 Newton. Right? Same string, it comes from here to here, 0.6 Newton. Pulley is smooth, no friction. So how do we ensure that there is no friction? See, after this system comes to an equilibrium, if you pull this and release it, pull one of the weights and release it, the system should go back to its original position. If it goes back to its original position, that means pulleys are smooth. See, let me pull this down, and if I leave it, system should go to its original position. Let me pull this and see. After pulling it, if I leave it, see, system comes back to its original position. So once they asked in the exam also, how do we ensure the pulleys are smooth? So you have to say, you displace the pulleys or weights by a certain distance and leave it. If it comes back to its original position of equilibrium, that means pulleys are smooth. Suppose if there is friction in pulleys, after you pull it and leave it like this, it will stay at this position itself. It will not go back to its original position. If it is going back to its original position, that means there is no friction in it. Right? So simple now, what are we going to do? We are going to mark this line and we are going to mark this line as well. See, understand the concept here. Here you have T1, here you have T2 and this is T3. Equilibrium of tri-forces T1, T2, T3 are in equilibrium. Okay. If I take T1 and T2, if you find the equivalent of T1 and T2, the resultant of T1 and T2, that should be equal and opposite to T3. That's how this point can be in equilibrium, right? T1, T2, if you get the resultant, that resultant should cancel this T3. So I'm going to draw a parallelogram having these two as adjacent sides and find the resultant. That resultant should be equal to this. That's how this point comes to an equilibrium, right? So how are we going to show the parallelogram? You mark this line and you mark this line as well, both side lines, and draw it proportionate to the weight that you are using. Here if you have 50 grams and 60 grams, maybe I can take 5 centimeter and 6 centimeter. Or 10 centimeters and 12 centimeters, right? Take a ratio, right? Take an appropriate ratio and draw the lines according to the scale that you have taken. Then complete the parallelogram, draw the diagonal, find the length of the diagonal and multiply by the scale that you have taken. That should be equal to the weight I have used here. It's a known weight, 90 grams. So the length should be equal to 90 grams. If I can get exactly 90 gram there, then I can ensure the system is satisfying. What we have done here verifies the law of forces equilibrium. Equilibrium of forces is verified. Mind you, like we may not exactly get 90 gram in the middle because of some errors. What are the errors we can have here? Pulleys, we assume it's frictionless, but there can be some friction. And we did not consider the weight of these plates, the chains. Right, so because of errors like that, there might be a small difference. 90 gram, if you are using 5 centimeter, 6 centimeter to indicate 50 grams and 60 grams, you must get 9 centimeter in the middle, but you might get plus or minus 0.5, 8.5 to 9.5, we should get it. Right, if we get that, we can say more or less it's verified. Okay, now shall we mark these points? Marking the point is also difficult because can you see there is a gap? There is a gap between the board and this thread or string. So you can't just press it like this and mark the point. You can't do that. Because when you press it like this, it may not be as the straight line as it was earlier. So we can't just press like this and mark. So how do we mark it precisely? We have two options. One option, you can use the set square. See, this is the set square. You can see there is a 90 degree here. There is a 90 degree in the set square. There is a 90 degree. So what we can do, keep one side of this 90 degree on the board like this, push it up until it slightly touches the thread. Push it up until it slightly touches the thread. The moment it slightly touches the thread, we can mark this point. Understand? Again, see. Keep it here, push it up. When the other side that makes 90 degrees slightly touches the thread, you can mark the point here. Likewise, you can mark 2 points and draw the line which will indicate this string. On the other side also you can do the same. 1 point, another point, and you can draw. But we have another better method for that. What is the better method? Using this strip of mirror. See, you have to keep the strip of mirror and you have to look perpendicular to the mirror. Look at this, right? If you look like this, when the string string and its image, if they look collinear, if you can see them at the same line, that means you are looking at it perpendicularly. Then you can put a dot on the paper such that the string, the dot and the image become collinear. Right, that means you are putting the dot correctly as an image of the string. Okay, look at this. Now, see, if I am looking at the mirror like this, no, I am not looking at it perpendicularly. I am not looking at it perpendicularly because there is a gap. So, if I adjust my side, I can see the difference. Can you see? Now, it is quite close. Can you see now? The line there is a small gap, still it is not aligned. Let me check carefully. Now look at this, students. I am looking at it perpendicularly. If I look at it perpendicularly, this is how I should see. The string, its image, they look collinear. They look collinear. They look at the same line. Then what can I do? I can put a dot on the paper. I can put a dot on the paper so that the string, the dot and its image are all on the same line. Right? Look at it. Look at the 2 points that I have made here. One is this and the other one is here. Similarly, the other side string also I have to mark. Now I have marked these 2 dots, so I can draw this straight line and the straight line will be proportionate. I have to take a scale and it has to be proportionate to the weight I am using here. It's 50 grams. If I assume 10 grams 1 centimeter, then I can draw it at 5 centimeter length. Similarly, on the other side, I'll show you the points that I have marked. One is here. The other one is here. If the points are not very clear to you, I will mark it with a pen and show it to you. But actually, when we do the experiment, we should not use blotting pens because then the dot will be too big. Then the accuracy will be lost. But here, since you have to see it more clearly, I'll show you with a pen. But remember, when you are doing it in the lab, it has to be just a dot with a pencil. A sharp pencil is what you have to use. I hope you can see the 4 points clearly. 2 points on this line, 2 points on the other line. Now we can draw the lines according to the scale, complete the parallelogram, measure the diagonal, multiply by the scale and see whether it's becoming equal to 90 grams that I have used here. If it becomes equal, then the rule of parallelogram of forces is verified. Shall we draw the parallelogram and see how it works? Students, you can see we have the paper where we have marked all those 4 dots. Now I am going to complete the parallelogram, right? Actually, we have to use the meter ruler, but I'm using a foot ruler just to show things more clearly to you. As it is a transparent one, you can see things more clearly. But actually, in the real experiment, you have to use the meter ruler. And in the exam also, you have to write it as meter ruler. You can write meter ruler or half meter ruler. Okay, not the foot ruler. Right. So, first let me draw the lines. That's how the 2 lines are. Now let's take an appropriate scale. You know, on this side I used 50 grams and on the other side I used 60 grams. 50 grams, shall we show it by 10 centimeters? Then I have to take 5 gram 1 centimeter. Then on this side I have to mark 10 centimeters. 10 centimeters. Let me mark 10 centimeters. That's where 10 centimeter is. 10 centimeter. Similarly, on the other side, I have used 60 grams. So 5 gram 1 centimeter means 60 grams. I have to mark 12 centimeters. 12 centimeters. This dot is exactly at 12 centimeter. So we can take this dot. Yes, this dot is at 12 centimeter. Now what I have to do is I have to draw parallel lines. Either you can use a compass to draw the parallel lines. If not, we can do this. See, keep the set square parallel to the line and support the other side of the set square with the ruler. Now move the set square, take it to this 10 centimeter point and draw the line. Extend the line. Similarly, the parallel line to the other side. Move the set square, bring it to the right point. Draw the line. Extend it until it intersects the other side of the parallelogram. That's how your parallelogram is complete. Now what shall we do? Draw the diagonal and let's measure the length of it. Let me draw the diagonal. The length of the diagonal we get 16.5 centimeters. 16.5 centimeter we get. 16.5 centimeter. Let's do the calculation. Look at this. The scale I took is 5 grams is given by 1 centimeter. Now I have got 16.5 centimeters. Multiply that by 5, you get 82.5 grams. 16.5 into 5 is 82.5 grams. Actually, I have used 90 grams in the middle, but we are getting 82.5. That is because of the errors that can happen in this experiment. Right? This is also a usual question in the exam. They ask you after the experiment, a student has got these values, which are slightly different from the actual values. What could be the reasons? There are multiple reasons for this. Reason number 1, we have taken an assumption that the pulleys that we used are frictionless and smooth. But actually you can't find pulleys with 100% friction free. There will be a little bit of friction, which we have neglected. Right? If at all we can use some lubricants or some oil and improve the frictionlessness, but you can't make it 100% frictionless. Right? So that's one reason why we may not get the exact answer. Second one, you remember the weight of those plates and the chains to hang those plates. We assume that to be nil. Actually, they will have some weight. They will have some weight. So if you want to get it precisely, what you must do, say in one side, on one plate, if I have added 50 gram, you need to measure the weight of that plate and the chain. Let's say that is 10 grams. With this 50, you have to add that 10 gram as well. And you have to draw for 60 grams. Similarly, on the other side, if I have kept 60 gram weight, In addition to that 60 gram, that plate and chain are going to be there. Let's say that is 8 gram, then that is going to be 68 grams. Likewise, we have to include the weight of those plates and chains as well when we draw the parallelogram. But what we have done, we have ignored those values and we have done this experiment. So that can be another reason why we don't get the exact answer. And the thread or string that we used must be inextensible and it must be light. That means it shouldn't have any weight, right? There might be a little bit of weight for the string and there might be sometimes a bit of extension on the string. All those are possible errors that can happen in this experiment. Understand? So, because of those reasons, we are not getting exactly the answer of 90 grams, but 82.5 grams with all these errors is quite close to the answer. So, we can say the parallelogram law is verified. What next we have to do, we are going to use this same concept, we are going to use the same parallelogram idea and find the mass of another object, an object with unknown mass. We are going to find it now. Shall we see how we are going to do it? Now we have verified the law of parallelogram. Now what we do, using the same concept, let's see if we can find the weight of an unknown object or mass of an unknown object, right? So same setup is here again. See what we are going to do. This is the unknown object that I have shown you, a stone actually. I don't know the mass of it. So let me keep that in the middle here. The moment I keep that there, it goes down. So what we should do, we should keep mass on the other two plates as well. I am keeping a 50 on this side and another 50 on the other side. It is in equilibrium. I will be able to complete a parallelogram, but look at this, this point is so high. So what happens, the parallelogram comes in this just, one part of the paper only. I will not get a sizable parallelogram, then the errors can be high. So what we will do, to bring it lower, I can't increase the weight of this. Let's reduce the weight of both sides. Let's reduce the weight of both sides so that it will come down further. Say I am putting two 20s here. So that's 40. What happens? Not so low. Still I can bring it down further. Let me keep 30 on the other side. I kept a 20 and a 10. 30. It has come down, but still better if I can bring it down further a little bit more. What happens if I make it only 20? Now look at this. I think I'll be able to use or optimize the usage of this paper because this point is here. The lines are these two. I should be able to use a proper parallelogram, a sizable parallelogram, and I should be able to get the answer. So look at this. This is 20 gram. So this line will have the tension of 0.2 Newton. This is 30 gram, so this will have a tension of 0.3 Newton. So 2:3. If I take it as 2 centimeter, this has to be 3 centimeter. If this is 10 centimeter, this has to be 15 centimeter. I can take an appropriate scale and draw these lines, complete the parallelogram, and I take the diagonal, the length of diagonal. If I multiply by the scale, I should be able to find the weight of this stone or mass of this stone. Right? So let's mark the points like I did earlier using the strip of mirror. Let me mark the 2 points on this side. Like we did earlier, I'm keeping the strip of mirror here. And I can see the line and its image collinear. I'll show you the points again. This is one and this is the other one. You can see that here. This is the other point. Let me check the other side now. Yes, I can see the string and its mirror collinear. I have marked the 2 points. You can see that. One here and the other one here. If you can't see the points, I'll mark it with a pen and I'll show it to you. But actually, you should not use the pen as I mentioned earlier. But to show it clearly to you, I'll use the pen and mark those points. Those are the 4 points that I have marked. So like what we did earlier, let's complete the parallelogram. Draw it according to the scale. Draw the diagonal. Get the length of the diagonal, and we can find the weight of this stone. Right? So shall we complete the parallelogram and see how much weight we are getting for this? So now let me complete the parallelogram with these points. Draw the lines. This time I have used 20 grams and 30 grams. On this side 30, in this side 20. So shall we take 10 centimeters to indicate 20 grams? Then on the other side, I'll take 15 centimeters. That means I'm taking a scale of 1 centimeter, indicate 2 grams. 2 grams. Then 20 grams will be marked by 10 centimeters. This is where 10 centimeter is. On the other side, we have 15 centimeter because I use 30 grams. 15 centimeters comes up to here. Let's draw the parallel lines. On the other side, extend the lines. That's how we get the parallelogram. Draw the diagonal that goes through the point of equilibrium. That's the diagonal. Let me get the length of that. I get exactly 20 centimeter, exactly 20 centimeter. 20 centimeter means 1 centimeter indicates 2 grams. So 20 centimeter should be 20 into 2, 40 grams. So the mass of that stone that I have used in this experiment must be 40 grams. But as we mentioned earlier in the previous diagram, there can be slight changes to this value. The actual value and the value we have got can be slightly different because of the same errors that I mentioned earlier. The friction, the weight of those plates and the chains that we used to hang. Because of these reasons, 40 might not be the exact value of the mass of the stone. Might be slightly different, but close to 40 gram. This is how we use the parallelogram theory. This is how we use the parallelogram theory and find the mass, unknown mass of an object. Right? So study this well, practice this well. This has been tested couple of times, right? With another experiment, we will meet again. So, the readings and calculations in this experiment, nothing much. I have already shown it to you during the experiment itself. Anyway, the scale we have used in the first section, 1 centimeter was 5 gram. So, length of OC 16.5, then the weight that we attach to the middle string must be 16.5 into 5, 82.5 grams. Similarly, so that is for the verification. Similarly, when we use the unknown weight, the scale we changed it to 1 centimeter equals 2 gram. Now, that unknown weight has to be given by 20 centimeter, 20 into 2, 40 grams. Right. So, nothing much as calculations in that. Now, let us see the past paper question that has come on this experiment. See, we have taken 2005 past paper question that has come on this section. Figure shows a set used in a school laboratory to verify the principle of parallelogram of forces. A. Smooth small pulleys. B. Vertical drawing board with a white paper printed on it, pinned on it. C. Light strings. D. Light scale pans. P, Q and R are weights. Give a list of other items needed to carry out this experiment accurately. What else do we need here? We need a half meter ruler or even a meter ruler. Half meter ruler. Then we need a glass strip or mirror strip, a thin mirror strip, mirror. Thin mirror strip, thin mirror strip. I think that's enough for us. You know why we use mirror strip. If you don't write mirror strip, you can write a set square. How do you test whether the friction of the pulleys is negligible? Remember, we already discussed that. You pull the middle weight and see whether it goes back to its original position. Pull, what's the name of the weight? Q. Pull Q downwards and release. If it returns to its original position, return to its original position, then the pulleys are frictionless. Pulleys are frictionless. Next. If the above arrangement is set up for you, briefly state the steps that you would adopt to verify the principle of parallelogram. So, setup is with all the weights and all. So, what we will do? Use the glass strip and trace, or let us say mark 2 points and mark 2 points to trace the strings. Do we have names for the parts of strings? No, okay. Strings. Remove the paper. And draw lines along the points in proportion to the weights. What are the weights? In proportion to P and R. P and R. Right. here we can say to trace the strings, which strings? Slant ones. Then all other parts are vertical, right? So, the two slant ones, those are the two that we have to trace. Proportion to P and R. Construct a parallelogram. With these two sides as adjacent sides. Adjacent sides. Draw the diagonal that goes through the point where the original two lines intersect. Thing is, we usually give names. If you don't give name, you are explaining wordings. Otherwise, we can say draw the diagonal OC. Right. Two lines intersect. This, measure the diagonal. Measure the length of diagonal and multiply by the scale. It should be equal to weight Q. Also, the diagonal must be vertical. That's a complete step of this experiment, right? Next, in order to carry out this experiment, light string should be used. What is the reason for this? Then only you can ensure the tension is same all over the string, right? To ensure the tension is same along the string. After completing the parallelogram correctly, a student noticed that the direction of the relevant diagonal was not exactly vertical. Give a reason for this. So, it has to be some error in the experiment. Most common error is the pulleys might not be completely frictionless. They might have had some friction, right? Pulleys have friction. Pulleys have friction. If the scale pans are not light, what should you do in order to carry out the experiment? Then scale pan also should be weighed. The scale of the weight of the scale pan should be added to the weights that are in the scale pans. The weights of the scale pans should be weighed and added with the respective weights. That is one option. The other option is to remove the scale pans and directly connect the weights. This setup is used by a student to find the weight of the stone. The relevant sides of the force parallelogram are shown in the figure. Evaluate the weight of the stone. Right, this is the figure we have. This is the figure we have. So, what we should do? We must complete the parallelogram. Right. So, how do we complete the parallelogram? Now, if we are using the ruler, Then look at this. Many students don't know how to complete a parallelogram. Look at this. This is the other side of the parallelogram. Then we drew the set square. Take your set square. Keep it along one side. Now take your ruler. Right, keep it like this. You understand what we have done here? Keep the set square along one line, and on the other side of the set square, you keep the ruler. Hold the ruler tight and you can move this set square. So, move the set square and bring it to this position. Where? This position. Keep the ruler tight, move the set square and bring it to this position. Now, what do you see? Set squares, this side is going through this point. Now, you can draw another line. Look at this. Draw this line. That means the side, this side of the set square you can draw. Draw that line. Now, that line is going to be parallel to this line. Similar way, you can draw the other side's parallel line also. Right? Using the set square and ruler, draw the parallel line also. Then you can complete the parallelogram. If not, the other option you have, look at this. If these two are the sides of the parallelogram given to you, then keep your compass. You take your compass, keep the base of the compass here and the pencil tip here. Get this distance, then bring the compass here and draw an arc. Similarly, measure this distance from here, draw the arc. Then you can complete the, so this is going to be the next point, right? You already have the 3 points. This will be the 4th point to draw the parallelogram. So, use those techniques and draw the parallelogram. Let me complete the parallelogram here. Since I am doing it in a computer, I will just draw a line parallel to this and move it here. Right. Then that will be the parallelogram. After drawing the parallelogram, you have to draw the diagonal that comes vertical as expected. Then you can see here they say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 divisions is 1 centimeter. Now I have to count how many divisions are here, right? In the exam, the scale that they gave, the graph sheet or the grid that they gave was sufficient for us to complete this, right? So you can count how many are there. It was 30 divisions we had here, 30 divisions. Then this is going to be 3 centimeter. This is going to be 3 centimeter. 3 centimeter. It's given 1 centimeter is 2 Newton. So weight has to be 3 centimeter into scale. You get 6 Newton as the answer. 6 Newton. Right? So this was the last part of that exam question. Right? So very simple. We have verified the law of parallelogram, and then using that law of parallelogram and using the same setup, how to find the unknown weight, I have shown you. We saw the practical how to do it, and then we have seen how this has been tested in 2005 exam paper also. Doesn't come so frequently, but you must be familiar to face this at any time. Right? So practice this very well. It should be answerable. It should be very easy for you in the exam. Next, let's meet up with another experiment in mechanics.